Okay, picture this. It's the end of the 19th century, and physics is in big trouble. A problem that seemed pretty simple had scientists completely baffled, and it was leading to a prediction so ridiculous it threatened to tear down everything they thought they knew about the universe. So this isn't just a physics lesson. It's the story of a scientific mystery that almost broke reality. And it all starts with a question you've probably asked yourself.
Seriously, that's it. Why does a piece of metal, when you heat it up, start to glow red, then orange, and then eventually white hot? It seems so basic, right? But it turns out that answering this question perfectly for any object at any temperature was one of the toughest puzzles in the history of science.
To really get to the bottom of it, scientists needed a perfect test subject, something totally idealized. They imagined an object that wouldn't reflect any light at all. It would just absorb every bit of radiation that hit it, and then re-emit that energy purely because of its own heat. They called this theoretical object a black body. You can think of it as the ultimate pure benchmark for understanding this kind of radiation.
And this graph is basically the scene of the crime. When scientists actually measured the light coming from a black body, they got this exact curve every single time. Along the bottom, you've got the wavelength of light, from the long infrared waves all the way to the short ultraviolet ones. And on the side, you have the intensity, or brightness. They could measure this curve with incredible precision, but for the life of them, nobody, and I mean nobody, could come up with one single theory that explained why the curve had this very specific shape.
So the greatest minds of the day, you can think of them as the detectives of classical physics, they got on the case, right? They were armed with these incredibly powerful laws from Newton and Maxwell, laws that had explained everything from the orbits of planets to the behavior of electricity. They were pretty confident they could crack this thing.
And two big theories emerged. First up was Wien's law. Now, it did a fantastic job explaining the curve for the short wavelengths, over on the blue and ultraviolet side of the graph. Then you had the Rayleigh-Jeans law, which worked perfectly for the long wavelengths on the other side. But here's the catch. Neither one could do both. It was like having two detectives, and each one could only solve half of the mystery.
And looking at the graph here, you can see the problem perfectly. Wien's law could nail this part of the curve, no problem. And the Rayleigh-Jeans law, it had this part over here totally covered. But that all-important peak right in the middle and the shape of the whole thing combined, nope, it was a complete mystery. Physics was totally stuck.
But things were about to get a whole lot worse. See, the failure of the Rayleigh-Jeans law wasn't just some minor miscalculation. When physicists followed its logic all the way to its conclusion, it led to something that was just, it was completely impossible. So here's what their math predicted. As you look at shorter and shorter wavelengths of light, as you keep moving left on that graph into the ultraviolet and beyond, the amount of energy a hot object should be putting out would just go up and up and up forever, with no limit.
The implication of this was, frankly, terrifying. It meant that any hot object, a simple glowing ember from a fire, the filament in a light bulb, should instantly blast out an infinite amount of high-energy radiation, mostly as powerful ultraviolet light and X-rays. They gave this insane prediction a fittingly dramatic name: the ultraviolet catastrophe.
According to the very best laws of physics they had, reality should be equal to infinity. But it's obviously not. You can turn on a light bulb without getting vaporized by a death ray. This wasn't just a wrong answer anymore. This was a giant, flashing sign that the very foundations of physics were fundamentally broken. Then, in the year 1900, a physicist named Max Planck decided to try something completely different. He later admitted it was an act of desperation. He came up with a solution that was so bizarre, so against all common sense, that even he wasn't sure he believed it at first. But it was an idea that would change everything. So Planck started with a few assumptions. First, he pictured the atoms inside the hot object as tiny little oscillators, just vibrating back and forth and giving off light. Standard stuff. But then came the crazy part. He proposed that these little oscillators couldn't just have any random amount of energy. No, their energy had to come in specific, individual packets. It was, as he put it, quantized. And he called these little energy packets quanta. A quantum is the absolute minimum indivisible unit of something. It's like a currency. You can have 1 coin or 2 coins or 100 coins, but you can never ever have 1.5 coins. This was a totally revolutionary way to think about energy. And this image right here just nails the concept. You see, classical physics saw energy as a smooth, continuous ramp.
An object could have any amount of energy it wanted. But Planck came along and said, nope, it's not a ramp, it's a staircase. An oscillator can only exist on one of the steps. It can be on a step, but it can never ever be floating somewhere in between.
So here's the takeaway. The core of his idea is this. Energy doesn't flow smoothly like water. It jumps. It comes in these discrete, chunky packets. And to emit that high-energy ultraviolet light, an oscillator would need to make a really big energy jump up that staircase. And because energy comes in steps, making a huge jump like that is just way less likely to happen. And that, right there, solved the ultraviolet catastrophe. And with that one simple, totally radical staircase rule, everything just clicked into place. Planck worked out a new formula based on this idea, and when he plotted it, it was a perfect match for the experimental curve. The same curve that had stumped the entire world of physics for years. The mystery was finally solved.
But what Planck had done was so much more than just solve a nagging puzzle. By introducing this idea of quanta, he had accidentally kicked open the door to a completely new and, frankly, bizarre reality. He had launched the quantum age.
I mean, the legacy of this discovery is just staggering. Planck's act of desperation didn't just fix the catastrophe problem, it introduced the single most important idea in modern physics, quantization. It laid the foundation for all of quantum mechanics, and every time you use a computer or a laser or a solar panel, you are using technology that is a direct descendant of this one breakthrough. Our entire digital world is built on the strange, stepped reality he uncovered, all because he wanted to understand why hot things glow.
And that kind of leaves us with a pretty mind-bending final thought, doesn't it? Planck showed us that the smooth, continuous world we see every day is just an illusion. Underneath it all, reality is grainy. It's built on tiny, discrete steps. So it really makes you wonder, what other fundamental rules of our universe are hiding just beneath the surface, waiting for us to find them?